Hello, my name is Riley Nold, and I'm a physics major here in the Reynolds Research Scholars Program at the University of Alabama, and I'll be presenting on my research related to first principles calculations of transition metal nitrides. So what are transition metal nitrides? It's essentially any compound where you have a transition metal highlighted on the periodic table over here, and nitrogen. So you can have binary transition metal nitrides, which are one transition metal and nitrogens, or you can have ternary transition metal nitrides where you have two distinct transition metals and nitrogen. These have many wide-ranging applications, but two specific ones are high mechanical stiffness and ceramic hard coatings. For example, titanium nitride has been coated onto drill bits to make them wear-resistant throughout use. We're also interested in these because they're significantly understudied. There's only under about 400 cataloged ternary transition metal nitrides. If you compare that to ternary transition metal oxides, there's over about 4,000 of those that have been effectively cataloged. So there's still a lot of room to look in what applicable properties these materials have. The material systems that I looked at this semester were cobalt nitride and manganese nitride, which have a face-centered cubic structure. When we talk about these crystals, one important thing to care about is the lattice constant. For simple cubic or face-centered cubic structures like this, that's essentially just measuring the width of a unit cell along the given cubic direction. So the goals of this project were to catalog transition metal nitride properties, such as crystallographic features relating to the lattice constant and things like electronic and magnetic properties. We're also interested in studying the effects of an expanded DFT plus U plus J model on our output data during these computations. So what was the computational process that was used? We first start with self-consistent field calculations. Essentially, we scan for multiple different possible lattice parameters for our unit cell, and then we look at what the cohesive energy of our material system was at that lattice parameter. We're then able to do this for the multiple different lattice parameters and get an energy versus unit cell volume graph, which we then fit to the Birch-Murnaghan equation of state. And we look at what lattice parameter gave us the minimum cohesive energy, as this is the equilibrium lattice constant that we would expect to see if our model is correct when we grow these things in the lab. It also gives us information related to the net magnetic moment of our material, so seeing whether or not it's magnetic, non-magnetic, etc. We also perform multiple different electronic calculations. For example, we get information about the band gaps of these materials. The band gap is essentially a measurement of the energy required to excite electrons from the valence band to the conducting band. If you have a high band gap, it means it takes a lot of energy to get the electrons in a conducting state, meaning that you're going to have an insulator. Whereas if you have a low band gap, it takes very little energy to excite these electrons to a conducting state, meaning that you're going to have a good conductor. We also look at something known as spin polarization, which we can calculate from the density of states. Essentially, we're looking at different energy levels, what kind of electron states are available. Specifically, we look at a reference energy known as the Fermi energy and see whether or not we have more available spin-up or spin-down electron states. And if there's a preference for spin-up versus spin-down, it means that our material is going to be better at conducting that type of electron versus the other. So I mentioned we used an expanded DFT plus U plus J model. Standard analysis of these materials just uses DFT, or density functional theory, but other transition metal nitrides that have been studied often have, they're considered highly correlated materials, so there's strong electron interactions that have to be accounted for. And to do that, we introduced two new energy terms during our calculations. The U term is an on-site coulombic term, so it accounts for strong electrostatic interactions between electrons and particular atoms. Whereas the J term is slightly more complicated, but it's known as the exchange interaction energy. Essentially is an energy derived from relative orientation of spin moments within the material. We then fix a particular U and J value and perform the self-consistent field calculation that I mentioned before and look at what trends we can see for different UJ values and what effect they have in our output data. Oopsies. So in terms of the initial results of characterizing these materials, we found that cobalt nitride and manganese nitride had lattice parameters of about 4.25 and 4.26 angstroms respectively. They were both found to be non-magnetic conductors with insignificant spin polarizations, which means although they are good at conducting, they don't have a preference for conducting spin-up versus spin-down electrons. When we look at the effects that the UJ values had on our output data, we'll be comparing lattice parameters that we calculated for each of these runs to these initially calculated lattice parameters here. So to give it a little idea of how we're going to visualize this data, as I mentioned before, we fix a particular value for U and J, and then we perform the self-consistent field calculation to get output data related to equilibrium lattice constant, magnetic moment, and cohesive energy. Then we compare this to the output data and see how it compares to our expectation values. Essentially, for lattice parameter, this means we're going to compare to the values I just mentioned before, whereas for the cohesive energy, we're going to compare it against the median energy for all of these runs. Then we plot out these difference values for the different possible U and J parameters we use. And when we do this, we want to look for low values of differences, as it means that this value of U and J was close to what we'd expect for our output data. For the lattice parameters, we can see that for cobalt nitride, a U and J value of around 2 electron volts and 1.5 electron volts respectively produce a small lattice difference from what we expected, as seen in the green region here. Whereas for manganese nitride, we found that there was a more linear dependence. And what I mean by that is along any line of slope 1, there's not much difference in the color, meaning that there's not an explicit dependence on U and J independently, but more of their difference, a value known as the U effective value. We found that as long as the U effective value was low, we were able to reproduce a small lattice difference as seen in the purple region here. In terms of cohesive energy, we see that this linear dependence arises again, meaning that we're only looking at particularly U minus J, or the U effective value. For cobalt nitride, we found that we were able to reproduce cohesive energies close to the median when U minus J was between 0.7 and 0.9 electron volts, as seen in the region here. Whereas for manganese nitride, it was found that we were able to reproduce median energy values between a region of 0.5 and 0.9 electron volts for this difference. In terms of magnetic moments, based on similarity of cobalt nitride and manganese nitride to other well-documented binary nitrides, we expect them to be non-magnetic. And we found that for cobalt nitride, we were able to reproduce this in the region seen here, where both U and J were low in terms of electron volts. And for manganese nitride, we found as long as their difference was low, we were able to reproduce this zero magnetic moment. To summarize the results, we cataloged the properties of 2 transition metal nitrides. We found cobalt nitride and manganese nitride to be non-magnetic conductors with no significant spin polarization. And we also established new trends related to the effective U and J values on transition metal nitrides. The next steps is we want to grow these materials in the lab. We do that by first creating thin films of these materials, and then through a process known as magnetron sputtering, and then testing the hypotheses about their predictions of what these properties of these different materials are going to have. We can use that doing an X-ray diffractometer to look at things like the lattice constant, or a physical property measurement system to look at conductivity. We're also interested in this ternary compound, cobalt manganese nitride, which can be thought as an alloy of cobalt nitride and manganese nitride, and we want to see if it has different properties from what we would expect the constituent binaries to have. I'd like to acknowledge the people you see here, Dr. Adam Hauser, my faculty advisor, Dr. Patrick Leclerc for his insight in studying these nitrides, my graduate student mentors, Ridwan Nayar and Strange Law, and the Heusler DFT subgroup. And if there are any questions, feel free to email me, or I can take those now.
How do you handle varying magnetic moments during the self-consistent field calculation?
Yeah, so that's a great question. So if we go back to more of the beginning here, when we look at the self-consistent field calculation, it fits a nice parabolic shape, but sometimes we get individual data points that are way below or way above, meaning that it's likely that our material is going to a different magnetic state. If we see this happening, then usually we try to fix the magnetic moment of our material at that particular value and run different SCF runs for those particular magnetic moments to see which ones have minimum energy. And the one that we go with is whichever one produced the minimum energy at its equilibrium lattice constant.
How do you plan to produce quality samples of these materials?
Sure. So as I mentioned before, we use a process known as magnetron sputtering. A little more information on that. So this is an off-axis method. Essentially, as was explained previously, we create a target of our sample that we actually want to make. We bring this into low vacuum in our ultra-high vacuum chamber, and then we basically use an argon plasma to be able to knock off atoms from our target, which then land onto our substrate. And because of the heater, they have enough thermal energy to settle into the correct crystalline formation. The off-axis method is used because it prevents direct bombardment of the ions on our sample, meaning that we're going to prevent degradation over time, because there could be damage for growth if you do an on-axis method.
Can you elaborate further on the specific type of DFT plus U plus J model used?
Yeah, so the specific type we used was known as LDA plus U type equals 1. So a standard model for DFT plus U plus J is what's known as the Dudarev model. However, this was a model that was outlined by Lichtenstein et al. So a lot of models focus on just the difference of U and J, but this model accounts for them independently, which is why we can't just look at the U effective value. We had to make these heat maps for multiple different possible U and J values.